The study of magnetic star-planet interactions, SPI, offers a promising approach to determining the magnetic fields of exoplanets. Sub-Alfvénic SPI models predict that terrestrial planets in closane orbits around M-dwarf stars can induce detectable stellar radio emission, manifesting as bursts of strongly polarized coherent radiation at specific planet orbital positions. Observations of the M-dwarf YZ Ceti, hosting a compact system of terrestrial planets, revealed 24 GHz detections of coherent radio bursts, with 2 bursts occurring at similar orbital phases of YZ Cet b, suggesting an enhanced probability of bursts near that orbital phase. The magnetospheric environment of the YZ Ceti system is modeled in the context of sub-Alfvénic SPI, indicating that YZ Ceti b can plausibly power the observed flux densities of the radio detections. However, the possibility of stellar magnetic activity cannot be ruled out without a well-characterized rate of non-planet-induced coherent radio bursts on slow rotators. YZ Ceti is thus a candidate radio SPI system, with unique promise as a target for long-term monitoring. The detection of coherent radio emissions associated with exoplanetary systems has motivated searches across MHZ to GHZ frequencies, as these emissions can probe the unknown magnetic properties of exoplanets. Proposed emissions result from SPI, where dissipated energy powers electron cyclotron maser (ECM) emission, occurring at the cyclotron frequency of the source region. Sub-Alfvénic radio SPI is expected to appear as bursts of coherent emission with strong circular polarization, lasting minutes to hours, with the angular beaming of the radio emission from the star-planet flux tube causing the emission to appear as well-defined bursts dependent on the satellite orbital phase. Recent results have revealed 150 MHz ECM emission from M-dwarf stars, potentially consistent with sub-Alfvénic SPI. However, confirmation is needed that a planetary satellite drives the radio emission. The radio flaring properties of inactive M-dwarfs across MHZ to GHZ frequencies are largely unknown, complicating efforts to exclude stellar activity as a cause of radio bursts. The detection of 24 GHz coherent radio bursts from YZ Ceti using the Carl G. Jansky Very Large Array (VLA) is reported, with the aim of identifying a system with coherent radio bursts in a very short period planet, enabling long-term monitoring to test orbital periodicity. Here is the combined summary of pages 3 and 4 of the research paper. The authors present a study on coherent radio bursts from the known M-dwarf planet host YZ Ceti, focusing on the characterization of these bursts and their possible planet-induced origin. The observations were conducted using the Very Large Array (VLA) at 24 GHz in 5 epochs, with a total on-source time of approximately 26 hours. The time series of all 5 epochs, phase-wrapped to the 2.02087-day orbital period of the inner planet YZ Cet b, reveals a range of radio emission behaviors. In the initial observations, the system was undetected in epoch 1, emitted multiple radio bursts in epoch 2, and produced slowly variable quiescent emission in epoch 3. The follow-up observations showed the star to be undetected in epoch 4, with a single coherent burst occurring in epoch 5. The Stokes V dynamic spectrum of epoch 2 reveals an hour-long coherent burst with nearly 100% right circular polarization, RCP, which is distinct from the weakly polarized flare that occurs 3 hours later. The authors infer a coherent emission mechanism based on the degree of polarization, as non-thermal processes typically exhibit less than 60% polarization. The brightness temperature of the RCP burst at 3 GHz indicates a non-thermal mechanism, likely originating from individual magnetic footpoints in the stellar corona. While the evidence cannot differentiate between plasma emission and electron cyclotron maser mechanisms, the latter is plausible for stellar planet-induced radio emission. The dynamic spectra of the detected bursts in epochs 2 and 5 exhibit a declining spectrum with the brightest emission observed near 2 GHz, characteristic of coherent emission. The authors focus on the RCP burst at 2.3 hours in epoch 2, which is the primary target of their search for coherent bursts induced by stellar-planet interaction. The study's findings have implications for understanding the radio emission mechanisms of M-dwarf stars and the potential role of planetary companions in inducing coherent radio bursts. Here is a combined summary of pages 5 and 6 of the research paper. The authors investigate the possibility of star-planet interaction, SPI, driving coherent radio bursts from the M-dwarf planet host YZ Ceti. They search for evidence of orbital modulation of bursts to test this hypothesis. A follow-up observation detected a 1-minute-long left polarized coherent burst with a peak flux density of 465 plus or minus 70 μJ, occurring about 2 hours earlier in the 2-day orbital period compared to the observed epoch 2 bursts. To assess the SPI mechanism, the authors estimate the magnetized environment of YZ Ceti using two fiducial wind models, Model A and Model B. Model A assumes an open magnetic field entrained by a strong radial wind, while Model B uses a weaker wind and a PFSS extrapolation to account for closed field near the star. Both models find that the innermost planets are within the sub-Alfvénic regime, allowing planetary perturbation of the stellar magnetic field to induce GHZ emission. The authors compute the power available to drive planet-induced radio emissions using the frameworks of reconnection and Alfvénic. These computations depend on the magnetic environment variables defined in the wind models, as well as the magnetic properties of the planets. The results are presented in Figure 3, which shows the predicted radio flux density due to SPI with YZ Ceti B for the two wind models and interaction frameworks. Under Model A, the Alfvénic predictions match the measured flux density of the bursts for a weakly magnetized planet, while the reconnection framework strongly overpredicts the measured bursts. In contrast, under Model B, YZ Ceti B could power the emission with the reconnection framework, even in the absence of an intrinsic planetary magnetic field. The Alfvénic scenario, however, requires a strong planetary magnetic field to power the detected bursts. The authors acknowledge that there are many uncertain assumptions in these SPI flux predictions, which can affect the accuracy of the results. Nevertheless, their calculations suggest that if the reconnection framework is accurate, then the bursts could be produced by YZ Ceti B through star-planet interaction. The research investigates the coherent radio bursts detected from the M-dwarf planet host YZ Ceti, focusing on the Alfvénic scenario and the potential planetary magnetic field. To evaluate the bursts' possible SPI nature, the authors modeled the flux density and examined their relative timing. They considered the synodic period, defined as the time it takes for the satellite orbit to return to the same position relative to the host magnetic field, and the half-synodic period, which defines a similar satellite position on the opposite side of the host magnetic field. The authors phase-wrap the time series of the RCP burst from epoch 2 and the time series of epoch 5 using three different periods for YZ Ceti B: orbital, synodic, and half-synodic. Although the epoch 5 burst does not show perfect recurrence at the orbital period, it exhibits a near-orbital recurrence, with a phase difference of approximately 2 hours. The synodic and half-synodic period phases do not align the epoch 5 bursts closer to the time of the epoch 2 burst, suggesting that the data cannot provide definitive evidence of SPI. The analysis also considers the possibility of ordinary stellar magnetic activity, such as flares, as an alternative explanation for the polarized bursts. The authors calculate the probability of seeing at least one event in the 3.6 hours associated with epoch 5, which is approximately 24%. However, the probability of seeing one burst, on two separate occasions within 2 hours of a given phase, is only 5.1%, indicating that the bursts could have no association with the planetary system. The mechanisms powering the emission remain inconclusive, and the authors categorize YZ Ceti as a SPI candidate, requiring further follow-up to discern the nature of the radio bursts. Figure 4 illustrates the phase-wrap time series of the portion of epoch 2 containing the RCP coherent burst and all of epoch 5, demonstrating the tested periods and phase errors due to uncertainty in the period measurements. The authors investigate coherent radio bursts from the known M-dwarf planet host YZ Ceti, exploring the possibility of star-planet interactions, SPI, as the cause. Two candidate SPI events are identified, with luminosities consistent with predictions for sub-Alfvénic SPI, but stellar magnetic activity cannot be ruled out. The bursts do not recur at an exactly consistent orbital phase, but display a greater degree of phase separation when considering synodic and half-synodic periods. This recurrence pattern may indicate an orbitally dependent window of visibility for observing beamed radio emission. To confirm SPI, the authors propose a twofold criteria: recurrence of radio bursts at a period dependent on the planet's orbit, and a low Poisson probability of randomly observing events within a narrow phased time window. This probability is based on an average burst rate determined by observing a wide range of orbital phases. Multipitch radio monitoring and complementary observations of the stellar magnetic field and planetary geometry are necessary to test for orbital modulation and distinguish SPI from stellar processes. The authors also discuss the stellar characterization of YZ Ceti, detailing physical properties such as mass, radius, and bolometric luminosity, as well as stellar rotation period and activity properties. Radio data analysis is performed using the VLA, with observations calibrated using the VLA pipeline and flux calibration with 3C147. The results are suggestive of SPI, but the ambiguity of the orbital phase difference and the possibility of stellar magnetic activity as a cause necessitate further observations. Longer-term radio monitoring and spectropolarimetric observations are required to determine the orientation of the star's large-scale magnetic field and test for orbital modulation. A deeper understanding of polarized stellar radio bursts across MHZ-GHZ frequencies is necessary to disentangle SPI signals from stellar activity. The proposed criteria for assessing and confirming magnetic SPI at radio frequencies provide a framework for future studies. Here is a combined summary of pages 11 and 12 of the research paper. The study focuses on coherent radio bursts from the known M-dwarf planet host YZ Ceti. Table 1 presents a comparison of properties between YZ Ceti, Proxima Centauri, and GJ 1151, including spectral type, distance, mass, radius, luminosity, and planetary system characteristics. Notably, YZ Ceti has a planetary system with 3 planets, and its coherent radio burst properties, such as frequency, burst duration, and polarization, are distinct from those of Proxima Centauri and GJ 1151. The authors employed radio interferometric observations using the Very Large Array (VLA) to detect coherent radio bursts from YZ Ceti. They used a combination of imaging and self-calibration techniques to improve the sensitivity and accuracy of their measurements. Specifically, they imaged the data using the CASA software package with web-projection, multi-scale imaging, and multi-frequency synthesis, followed by self-calibration using the GainCal command. This process enabled them to achieve high-quality images of the radio bursts. Figures 5, 6, and 7 display the resulting images, which reveal the presence of coherent radio bursts from YZ Ceti. Figure 5 shows the self-calibrated image of epochs 1 to 3, demonstrating the improvement in flux density uncertainty after self-calibration. Figures 6 and 7 present images of radio bursts in epochs 2 and 5, respectively, after subtracting background sources from the visibility data. The authors highlight the significance of their results, including the detection of highly polarized coherent radio bursts from YZ Ceti, which suggests a strong magnetic field and potential planet-star interactions. The study provides new insights into the properties of M-dwarf planet hosts and their potential for hosting habitable planets. The researchers present a detailed analysis of coherent radio bursts from the M-dwarf planet host YZ Ceti. They utilize 724 GHz images of YZ Ceti in Stokes I and V during the left polarized coherent burst in epoch 5, measuring an average flux density of 468 plus or minus 70 μJy, I, and 441 plus or minus 55 μJy, V. The team calculates the standard deviation of the imaginary component to estimate effective noise levels in the time series, which includes thermal noise, RFI, and side lobes of imperfectly subtracted background sources. For 3-minute integrations, they measure noise levels of 5580 μJy in the Stokes I time series and 3750 μJy in Stokes V. The elevated noise levels in Stokes V are likely due to RFI, while Stokes I noise levels are affected by both RFI and imperfect background source subtraction. The VLA's compact configuration enhances these effects. The researchers also present a 24 GHz time series of YZ Ceti during epoch 2, with 3-minute integrations. They calculate the degree of circular polarization using a maximum likelihood approach, deriving a 68% confidence interval. The coherent burst at 2.3 hours exhibits right circular polarization of 93.5 plus or minus 2.6%, while a smaller event at 5.1 hours is also a likely coherent burst with strong left circular polarization. To identify bursts, the team requires a flux increase of greater than 3 sigma during the burst compared to before or after the burst. They measure or place an upper limit on quiescent emission levels using images of the full epoch duration after background source subtraction. Weakly polarized, non-thermal, slowly varying quiescent emission on M-dwarfs is typically attributed to incoherent gyrosynchrotron emission. The researchers assess the burst's degree of circular polarization using a maximum likelihood approach, estimating RC and constructing a 68% confidence interval. They assume RR and LL are Gaussian distributed, obtaining the standard deviation for each. The results provide insights into the properties of coherent radio bursts from M-dwarf planet hosts like YZ Ceti. Here is a combined summary of pages 15 and 16 of the research paper. The authors present a detailed analysis of coherent radio bursts from the known M-dwarf planet host YZ Ceti. Figure 9 shows a 24 GHz time series of YZ Ceti during part of Epoch 5, with 20-second integrations. The top panel displays Stokes I and V flux density, while the bottom panel shows the degree of circular polarization, derived through a maximum likelihood approach. The coherent burst exhibits left circular polarization of 73% plus or minus 16% in the time bin with peak flux density. The authors generated a probability distribution function, PDF, for obtaining the data in terms of model parameters SI, Stokes I flux density, and RC, then marginalized the distribution across SI to obtain a PDF for RC alone. The black line in figures 8 and 9 shows the value of RC at which the PDF peaks, and the gray confidence interval shows the range of RC that lies from 0.16 to 0.84 in the cumulative distribution function. Dynamic spectra were produced for all of Epoch 2 and for a short time period surrounding the Epoch 5 burst, using base lineaveraging code. The flux density uncertainties quoted in the caption are calculated using the imaginary component of the dynamic spectrum. The peak flux densities in Stokes V for the Epoch 2 bursts at 2.3 hours and 5.1 hours both exceed 5 sigma, as does the Epoch 5 burst. The authors investigate the stellar magnetospheric environment to determine whether star-planet interactions could have powered the observed polarized radio emissions. They consider two models: A magnetosphere defined by a radial isothermal stellar wind, and B, a potential field source surface, PFSS, extrapolation of typical M-dwarf Zeeman Doppler imaging measurements. The radial stellar wind solution is formulated using a Weber wind model, which solves the ideal magnetohydrodynamics problem in spherical coordinates for an axisymmetric equatorial wind propelled by a rotating star. The authors acknowledge the limitations of these models, noting that the magnetic field and wind environments of low-mass stars are very uncertain. The radial stellar wind solution overestimates the magnetic field at the planet location, while the PFSS extrapolation may underestimate the strength of the magnetic field at planetary distances from the star. The research paper explores the stellar wind properties of the known M-dwarf planet host YZ Ceti, focusing on its potential to generate coherent radio bursts. The study utilizes a two-dimensional isothermal wind model that incorporates the stresses of the ionized wind on the magnetic field anchored to the rotating star. The authors employ an isothermal wind solution, which is a subcase of the general polytropic approach, and use a compromise mass loss rate based on Rossby numbers and the low rate of ArXiv, a star with similar physical properties but weaker magnetic field strength. The paper presents two fiducial models, Model A and Model B, which differ in their assumptions about the magnetic field strength and mass loss rate. Model A assumes a coronal temperature of 0.25 keV, a constant mass loss rate of 10 to the power of 13 m, Sun year (1), and a radial field of 220 G. Model B, on the other hand, uses the same coronal temperature and radial field but a lower mass loss rate of 510 to the power of 13 m, Sun year (1). The authors also utilize the measured large-scale field topology of ArXiv, a slowly rotating late M-dwarf with a similar physical properties to YZ Ceti, as no such measurements are available for YZ Ceti. They scale the measured magnetic field of Pro-X-Sen based on the Zeeman broadening measurement of YZ Ceti, achieving an average field flux strength ratio of 0.1 and thus an average radial surface field of 220 G. The paper's findings are presented in figures 11 and 12, showcasing the magnetic properties and stellar wind properties in the two fiducial models. These figures reveal that the planetary system is likely interacting in the sub-Alfvénic regime with the host star, with radial wind velocities of 600,700 km/s-1 near the location of the planets. The total pressure from the assumed stellar wind is below the magnetic pressure of a 1G field, indicating that appreciable planetary magnetic fields on these planets are likely to carve out their own planetary magnetospheres. The closed field region used for the PFSS model is denoted by the gray region at left in Figure 12. The study highlights the importance of understanding the stellar wind properties and magnetic field strength in interpreting the potential for radio bursts from known M-dwarf planet hosts. The findings suggest that the interaction between the stellar wind and planetary magnetic fields plays a crucial role in determining the generation of coherent radio bursts, providing valuable insights into the complex interplay between stars and their planetary systems. The research paper explores the potential for magnetic interactions between the M-dwarf star YZ Ceti and its planets to power coherent radio emissions. To model this interaction, two distinct models were developed. Model A, which assumes a simple, dipolar magnetic field and a typical wind model, and Model B, which incorporates a more realistic stellar field and a lower mass loss rate. Model B uses a potential field source surface, PFSS, extrapolation based on Pro-X-Sen's field topology, scaled to yield an average large-scale radial magnetic field of 220 G at the stellar surface. This model also considers a lower mass loss rate of 0.25 m, comparable to the upper limit on Pro-X-Sen's wind and consistent with the predicted rate from the relation between X-ray surface flux and mass loss rate. The study estimates the available power released by magnetic reconnection and Alfvén wanes, two frameworks used to describe the energy dissipation in the interaction between the stellar wind and the planetary magnetosphere. These expressions depend on geometric factors, the velocity of interaction, magnetic field strength, and mass density of the magnetized flow. Focusing on YZ Ceti b as the closest in planet, the authors calculate the power available to generate radio emissions using both models A and B. The geometric factor is assumed to be 0.5, and the interaction strength is set to 1, based on the likely conductivity of the planetary obstacle through its magnetosphere or ionosphere. The last variable in the power expressions is the planetary obstacle radius, RO, which is defined by the size of the planetary magnetosphere or at a minimum the radius of the planet itself, assuming a thin ionosphere. The radius of the planetary magnetopause is determined using the pressure balance between the supposed planetary field and the wind. In conclusion, the paper presents a comprehensive analysis of the potential for magnetic interactions between YZ Ceti and its planets to generate coherent radio emissions. The two models developed provide a framework for understanding the complex interplay between the stellar wind, magnetic fields, and the planetary magnetospheres, shedding light on the possible mechanisms behind the observed radio bursts. Here is a combined summary of pages 21 and 22. The authors investigate the possibility of coherent radio bursts from the M-dwarf planet host YZ Ceti, focusing on the star-planet interaction (SPI) scenario. They assume a planetary dipole field strength (RP) ranging from 0.89 r circled plus to 1 r circled plus, and explore a range of dipole field strengths from 1 G to 10 G. The energy available to power auroral radio bursts is computed using the reconnection and Alfvén wing prescriptions, considering both Model A and Model B wind environments. The authors derive an equation, equation 3, to calculate the obstacle radius, RO, and use it to determine the energy available for radio bursts. They then convert this energy to a possible burst radio flux density using equation 4, which depends on the radio efficiency factor, emission bandwidth, distance to the star, and beaming angle. The results of these calculations are displayed in Figure 3, which shows the predicted flux densities for star-planet interaction. The authors highlight the dependence of these predictions on unknown properties, such as the stellar mass loss rate and stellar field strength. They explore the range of mass loss rates consistent with the SPI scenario and the dependence of the SPI power on the assumed stellar magnetic field. Using their isothermal wind solution, the authors investigate the impact of the assumed mass loss rate on the Alfvénic Mach number at the position of the planets around YZ Ceti. They show that the Alfvénic Mach number grows with the assumed mass loss rate, and the planets will become super-Alfvénic at higher mass loss rates, figure 13. The authors approximate the Alfvénic Mach number using equation 5, which depends on the velocity and field conditions evaluated at the location of each planet. The results imply that if the detected bursts are powered by sub-Alfvénic star-planet interaction, the corresponding planet must be within the Alfvén surface of the stellar environment. The authors conclude that YZ Ceti's mass loss rate should be within the bounds derived from their analysis, likely less than 13.5 times the solar mass loss rate, using their more realistic Model B stellar field topology. Here is a combined summary of pages 23 and 24 of the research paper. Scaling the stellar magnetic field strength in models A and B reveals that increasing the surface radial average field strength linearly scales the field at the location of the planet and similarly scales the minimum predicted star-planet interaction, SPI, flux density as a function of planet field strength. This is evident in the flat regions of Figure 3, where the turning points shift towards higher planet field strengths, encoding the balance between stellar and planetary fields. For Model A stellar field increase of a factor of 2 or 3 places flux density predictions above the measured bursts, underscoring that Model A overestimates the stellar field strength by not accounting for closed field structures. In contrast, for Model B, an increase in the field strength of a factor of 2 or 3 pushes both the reconnection and Alfvén wing predictions to higher values, with the Alfvén wing prediction becoming consistent with smaller but non-negligible planetary dipole fields. The radio data used in this publication are available through the NRAO archive, and the codes describing the model's stellar wind implementation are available upon reasonable request. The authors acknowledge the contributions of several individuals and organizations, including Baptiste Klein and Julian Morin, for providing spherical harmonic coefficients for ProX. SENS field topology, and the National Science Foundation, the National Radio Astronomy Observatory, and the European Space Agency for funding and support. This research was supported by the National Science Foundation under grant number AST 2,108,985 and AST 2150703, and the authors declare no competing interests. The authors' contributions include identifying the target, developing models of the stellar environment, calculating star-planet interaction flux density predictions, developing the observing strategy, reducing and analyzing radio data, and interpreting results. The version of record of this article is available online at the publisher's website. Here is a combined summary of pages 25 and 26. The paper discusses the detection of coherent radio bursts from the known M-dwarf planet host YZ Ceti. The authors draw upon previous research on radiometric Bode's law, magnetic energy fluxes, and exoplanet-induced radio emission from M-dwarfs. They cite various studies on the population of M-dwarfs observed at low radio frequencies, the TESS view of LOFAR radio-emitting stars, and the search for exoplanets around M-dwarfs. The authors also reference research on planet-induced radio emission from the coronae of M-dwarfs, including Proxima Centauri and OMIC. They discuss the detection of faint, polarized flares from UV Ceti and ultrawide-band detection of coherent radio bursts on M-dwarfs. Additionally, they mention the implications of a flare-type IV burst event from Proxima Centauri for space weather. The paper builds upon foundational research in stellar radio astronomy, including the work of Goodall, Dulk, and Austin. It also draws upon studies on stellar coronal magnetic fields and star-planet interaction, as well as modeling the radio signature of the orbital parameters, rotation, and magnetic field of exoplanets. Furthermore, the authors reference research on the H-alpha emission of nearby M-dwarfs and its relation to stellar rotation, as well as the origin of electron-cyclotron maser-induced radio emissions at ultracool dwarfs. They also cite studies on the Mussels Treasury Survey, FUV flares on active and inactive M-dwarfs, and the M-dwarf ultraviolet spectroscopic sample. The paper utilizes data from various surveys, including the Gaia Data Release 2, and references studies on constraining M-dwarf parameters, such as effective temperature, bolometric luminosity, mass, and radius. It also draws upon research on transiting exoplanet survey satellites and astronomical data analysis software and systems. The paper discusses the coherent radio bursts observed from the M-dwarf planet host YZ Ceti, a known M-dwarf star. It is known for its strong magnetic activity and flaring behavior, which can significantly impact the surrounding space environment and potentially affect any orbiting planets. The study aims to understand the stellar magnetic field and its impact on the star's rotation and wind properties. The research utilizes various methods such as Zeeman Doppler magnetograms, Hubble Space Telescope Lie alpha spectra, and astropy packages to analyze the star's magnetic field, wind, and rotational properties. The study also employs data from the Palomar, MSU Nearby Star Spectroscopic Survey, CARMENES search for exoplanets around M-dwarfs, and M-Earth Transit Survey to gather information about the star's rotation periods and magnetic properties. The paper highlights the importance of understanding the magnetic field of M-dwarf stars, as they are key components in the study of stellar winds and rotation. The magnetic field plays a crucial role in determining the mass loss rate of the star, which in turn affects the habitability of any surrounding planets. The study suggests that the observed coherent radio bursts could be indicative of strong magnetic activity and large-scale magnetic fields, similar to those observed in Jupiter and other magnetized planets. The paper also discusses the limitations and assumptions made during the study, including the use of simplified models for the stellar wind and magnetic field. Future work includes refining these models and conducting further observations to better understand the relationship between magnetic activity, stellar winds, and planetary habitability.